First of all, I appreciate everybody showing today. I know when you see sponsor, it gets a little scary, and oh no, he's going to sell me anything. I promise this isn't a sales pitch. First of all, thank you for attending. I love being in New York. It's been a while since I've been here. So much energy. I know a lot of you came from out of state as well. Today I'm going to be talking about why your Kubernetes cluster will fail. We all know this is inevitable, and I want to share lessons that we learned, not only myself but colleagues in doing various testing with 1 million real-world incidents. I tried to convince them to let me do the Austin Powers meme with $1 million, but I wanted to keep it a little more serious today. I'm John Slaughter. I'm a solutions architect at Commodore. Let me tell you a bit about myself so you know who's talking and why you should listen. First, I'm a senior solutions architect. I've been in the Kubernetes space for just shy of a decade, working for various cloud providers as well as SaaS providers. I've been in the room when big things have happened, whether that's your favorite streaming service going down or whether that is your teenage daughter's favorite pop artist breaking the internet with her ticket sales. So I've seen the good, the bad, and of course the ugly when it comes to Kubernetes setups. And of course, finally, I can do a perfect impersonation of somebody that knows what they're talking about. So keep that in mind as I present. Now, I do have you guys for a good amount of time here, so let me tell you what I'm going to talk about and what agenda is in front of us. First, I want to talk about the reactive chaos that exists today, the kind of immature nature of some setups, before we start getting into the run phase of working with Kubernetes clusters and remediations. I want to talk about the 1 million incident experiment we did where we tested various issues throughout Kubernetes clusters. We'll talk about the 6 failure categories, or where we categorize these various issues that have occurred. I'll go over some example incidents as well so that you guys can kind of see a bit of the data that we pulled and the various fun scenarios we went through. And then we'll cap it off talking about the AI SRE evolution, which is, of course, with the advent of AI, has been an increasingly major thing that we're seeing in our modern day. So let's start off by looking at this fun little flow chart. To some people, this may look simple. To others, it may look very complex. In my opinion, I just think it looks very boring and very awful to deal with. What you're seeing here is a flow chart where when people want to troubleshoot their Kubernetes clusters, they look at the error and they say, okay, here I am in my adventure. If it's this, do this. If it's that, do that. And you end up following this almost like story to follow the flow chart and hoping that you'll end up at a remediation or an actual fix to whatever issue you have running within your Kubernetes cluster. I'll be honest, it's mundane, this is very vanilla, and Kubernetes troubleshooting, it really sucks. It gets way worse when it's 3 a.m., a lot of pressure is on, you've got that P0, pager duty goes off, and everybody's relying on you to fix the issue. And then you have to deal with these charts. It's also worth noting that real-life troubleshooting and flows are even more convoluted and sprawling than what you see here. When it comes to the actual issues you see, even if this does look complex, the issues are typically far more complex. So let me tell you a little bit about the experiment we did along with some of our high-level findings. So I'll have a spoiler or two in here as well. So here was our goal. We wanted to create a deterministic runbook. That is, we wanted to map common Kubernetes issues to various root cause analysis solutions. That way, whenever we had recurring issues, we could apply the same fixes and ultimately get to resolution much faster. We did this by taking 1 million different real-world incidents. Commodore, the company I work for, our whole mission is to help lower mean time to recovery. So we're working alongside companies all day long of various sizes, of various industries, to remediate their issues. So we had access to a large data set to run our fun little experiment. Now, one quick spoiler finding is that we found out a majority of these, an overwhelming amount of these, fell into 6 categories, which was great when you can narrow a number like 1 million down to 6 categories. But then we were a little surprised, because even though we got them down to various categories, the categories didn't mean a whole lot. They lied. If we said, hey, this resolution typically happens with this category, That was not the case. Let me quickly talk about what those categories are, and then I'll explain more about how it didn't really work out. So you can see here, these are 6 major categories. Some of the issues, in fact, a lot of the issues fell into multiple of these categories. The first one, top left, as you see, is resource exhaustion. You can think of that as simply having nodes with not enough compute to run the various applications that you are trying to host. So think kills, CPU throttling. You may have disk pressure, anything of that nature. Again, anytime a node or VMs didn't have enough compute to run your deployments. In the upper middle, you have images and other deployments. Maybe you're having an image pull back off. Maybe your registry has limits on it and it's not able to pull additional images. Maybe there's a syntax error and that image you're trying to pull doesn't exactly exist. We have configurations and secrets. Maybe your security team did a rotation, so any hard-coded secrets for whatever reason are now not working. You have authentication issues. You have other various configurations. Think your config maps or anything of that nature. Those things may drift in terms of how they're configured and cause outages and other problems. The bottom left, this is an interesting one. We had cascading failures. Think of this as you had one particular issue, and because it occurred, multiple other almost irrelevant workloads were affected, basically victims of a single issue. Again, that's one of the categories where a lot of things fell into multiple. We have storage and persistence. In Kubernetes, you have persistent volumes, and then you have the claims, and then you have to do the fun dance of making sure that your workloads land in the same availability zones as their associated storage. You could have other storage-related things, CSI driver issues, attachment issues, corrupted data, things of that nature. And then our final category we ran into commonly was the application versus infrastructure. This was kind of a whodunit game. Is this the problem of your developers, your software developers, and their code itself? Or is this a DevOps issue, something related to the actual infrastructure, the VMs, the nodes, the scaling behavior, things of that nature? Maybe you're doing more complex infrastructure or incorporating GPUs. This becomes very complex when trying to figure out all these various issues. So here were our categories, but we didn't find a good pattern to this resolution always fits this category. So let's take a deeper dive into actual examples from this experiment. I told you 1 million. I'm going to narrow that down to 3 in here just to save you guys' time and sanity. Let's take a look at this first one. I know I've broken a big rule of PowerPoint and put way too many words on a slide, but I'll try and simple this down for everybody today. You'll see at the top these little green circles. Those are next to deployments. On the top, we have one deployment called cache loader. Just below it, we have another called event processor. These two are interesting because if you look just below them, you'll see a reason, you'll see a last state, a reason for that last state, and an exit code. They are identical for both of these workloads. That is, they've both in a terminated state, they have both been killed, so that's out of memory, and they have exit code 137. This was great for our experiment to find 2 identical looking workloads having the same exact error because our hypothesis would be we could find a solution to the first, apply it to the second, and then we would have a great solution in a run book. That way, if we ever ran into this in the future, apply that solution much quicker, lowering our MTTR, our mean time to recovery, and then we're good. That didn't pan out so well in this case. In the first example, we dug into the logs a little deeper and saw some interesting characteristics of this particular error. In this case, the top one, whenever it was scheduled to the node, it killed immediately. It never came up to run. It never started. Went into a crash loop, back off immediately. So we knew all we had to do to fix this was to increase the memory limit. And that's exactly what we did. We gave that particular workload access to more memory. The scheduler scheduled it to a node that had that available, and then it was up, running, and good. Now, again, our hypothesis would be I could apply this to the second one, and we'd be good to go. We did the same thing to this event processor, the bottom one, added more memory, thought we were good to go, and then about 25 seconds into deployment, it crashed out of memory, which was a little confusing. Like, how could this be any different? Well, we looked a little deeper, and you can see towards the bottom, it says it originally ran for 13 seconds. So unlike the first one, instead of being killed immediately, this one actually started running 13 seconds before it was finally killed. Now, obviously, this indicated a gradual memory leak or something was wrong on the code level. So what we did is we fixed the application code to release that accumulated data. Now you're probably wondering, cool, these are different. Why is this important? Well, it made it very difficult to go back to what we wanted to do and create a run book, create strategies to do this much faster, because even though they looked the exact same, they had different fixes. Let's look at, I have two more here. I'll get through them fast, I promise. So we've got this table here. This table shows 6 different pods in various states. 3 of them are running, 3 of them are in crash loop back off, and 4 of them are having various restarts, which means that in reality, the one that's running and is being restarted is probably just flapping back and forth between crash loop back off and a running state over and over again. So we effectively have 2 running and 4 with issues. Now these are data pipelines. These the top 3 are part of an order processing pipeline, and the bottom 3 are part of a data analytics pipeline. So let's go through that same exercise. These are very similar. Can we apply the same fixes for both of these? So in the first one, we have a notification service. It's sending a request to the order processor. That is sending a request to Redis cache. So we dug into the logs. We said, how can we remediate this issue? Why are 2 of them crashing? And we actually found that the Redis cache service had a selector on it. It was looking for an app called Redis. But the pod itself had a label called app Redis cache. So a simple syntax error, somebody mislabeled it, and the actual network service was looking for something with a completely different label. Obviously, that caused the service to resolve to no endpoints. It couldn't contact it. And because of that, all the way down the chain, it broke. This is interesting for 2 reasons. One is the issue lied within the running pod. So when we're troubleshooting at 3 a.m., trying to figure out what's going on, our first instinct is always, let's look at the broken ones. Let's look at the ones in crash loop back off, the ones not running. It's not a first thought to let's look at the one that's healthy, up and running, and good, even though that is where the issue lied. Again, we took this solution we found to the first pipeline, and we applied it to the second one. You see here in the second one, it's the same type of structure. We've got a dashboard API. It's communicating with the ETL worker, and then that's finally communicating with the data store that is in a running, healthy state. If we apply the exact same remediation, well, the labels are going to be different. That's fine. It's not that hard to see what they are. But when we looked at these labels and these selectors, they were okay. There wasn't a problem with them. So here we are chasing another edge case, or so we thought, and we found that it actually just had malformed JSON. So somebody had put a comma trailing a value within a JSON. This caused, obviously, it to not to have a decode error, and it could not actually follow through with the network connections. So the net of this really is that, A, the real cause is rarely the crashing pod. These were both issues existing on running pods, and they were different issues from each other. Last one, and then I'll kind of get into the summaries and more findings from all of this. These are 2 different pods that have liveness probes failing. Right? These liveness probes are great so that you can understand what ports are listening, what actually has healthy services running on them, happy applications running on them. And in this case, again, both liveness probes were failing. In deployment number 1, we saw that it had an infrastructure misconfiguration. The liveness probe was listening on the wrong port. In this case, a Python server was on port 8080, and the liveness probe was looking at 9090, which obviously didn't have anything listening there. So it declared a problem where there really wasn't one. It was just in the wrong place. So we changed that port from 9090 to 8080, and everything was up, running, and healthy like it should have been. In the second, we had an application bug. So not only is this different in terms of how to fix it with the ports, but this is a different team that would handle it, right? We're on the application layer. The event showed that it had a context deadline that was exceeded. We had a warning that report generation was blocking the main thread. And ultimately, we had to move the blocking operation to a background thread. This is something that the application team would need to handle. The question then becomes, when this happens, who are we escalating to? Which team does it go to? Does this go to the infrastructure team? Does it go to the application team? And how do you put this in a flow chart, right? Is it supposed to say, check the ports, and if not, over here? Suddenly this flow chart that is simple is becoming quite the web with many edge cases. So let's look at what lessons we learned, not only from these 3 that I showed you today, but from the million incidents that we analyzed. First, this was obvious. Production environments, they are very complex. It is very difficult to put simple fixes and simple flow charts where something is always going to work. There's many variables in which we often don't account for, especially in changing environments. One where we're constantly releasing new features, updating things, making them more efficient. All of these changes add a lot to complexity. We found that available tools vary significantly between organizations. So different companies have different monitoring tools. They're using different levels of monitoring tools, the basic ones that maybe are native to their cloud provider, or third-party ones with special flashy features that can help them investigate faster, for example. But all of that really changes the variability in terms of how fast they can recover. We saw this all the time, but we saw this a lot in the last 3 issues I showed, but the same error often showed different resolutions. Again, can't really make a good flow chart, especially when there's 3, 4, 5 different solutions to a single error, and it really depends on the context of it. Scale erodes predictability. The larger your company is, the more this is going to become unpredictable. We found it very simple to spin up one cluster with a couple nodes and a couple deployments and monitor and figure it out in a test environment. But once we got to that enterprise scale where we were managing a dozen different clusters, hundreds of nodes and thousands of deployments, it gets out of hand very fast. And a lot of troubleshooting is done by individuals. So they've got to have the expertise to be able to handle all of these various cases, often on their own or with very limited help from others, and hoping you have the best SRE for the job, so to speak, to resolve them. Context is essential. In my first example, that looked exactly the same with the kills, with the fact that they looked the exact same, but they had different resolutions. The difference was one got killed immediately and one ran for 13 seconds before it got killed. That is context that was required in order to remediate the issue. So back to this run book, right? Our goal was to make the ultimate run book, the run book that could chart out every single Kubernetes issue that you could ever even dream of seeing, or not dream, have nightmares of seeing, rather, and be able to get you to a resolution fast. Honestly, we had major problems with this. The divergence between the 2 incidents was too high to script. Every runbook edit that we added caused a regression somewhere else. It was almost like plugging a hole in the ship that was leaking, just introduced a new hole. And the ship continued to sink. And then, of course, when 80% of the cases have a unique twist, it's not really an edge case anymore. So it was like edge case after edge case. What about this? What about that? And bam, now 80% of them were edge cases. So the question is, did we fail? Am I here standing up here saying, sorry, we looked at 1 million and we couldn't create that dream run book? Well, no, this is a conference talk, so we'll tell you how we didn't fail. Here was our solution. You've been hearing a lot about this lately. A lot of companies are getting into this, and we definitely are. Agentic AI. Now, let me say more about that. An agentic AI doesn't require a flow chart of if this, then this. Sure, that context can be helpful. But the real context lies in all the logs, all the data, all the things that require SREs to take hours and hours of their day to look through, to understand, and to piece together. It's not linear. And that's where agentic AI thrives, is the ability to ingest large amounts of context and data, at least relevant context, to be able to get to that resolution. We can also input things like organizational knowledge bases and architectural blueprints. Earlier I mentioned how various different companies have different ways they operate. They have different hygiene for their data and their logs. They have various different ways they handle their issues, and their applications may be designed much differently than each other. So it's very vital that we utilize things like blueprints and your company's proprietary way of handling them. And that's something you can inject into agentic AI and have create results. The last thing is to have multi-agent with multiple agents working with narrow focus. We're all very familiar with going to a simple LLM like ChatGPT, typing what we want and getting an answer back. But really the power comes with agents that have those harnesses. They have that context in their zone. So what we worked on is having ones that were experts in various facets of Kubernetes. As you can imagine, think like an agent that was specialized in Helm, another one that was specialized in CD tools like Argo or Flux, others that were specialized in metrics, so it can measure CPU and memory to see if that was an issue. All of these things are doable with agentic AI that a flowchart simply could not do. And the context took up hours of engineering time. So we set out to create this agentic AI. How do we create an AI with various agents that anybody could utilize, any company could utilize, do some tweaks and tailor it to your company's needs so that whenever you inevitably do have that issue, instead of going to the run book which we sought out to create, you would be able to have natural language to be able to inject that data into AI and be able to figure out your company's proprietary needs. And this is what we created. We called it Cloudia AI. This is our agentic AI at Commodore that is in production today, that many enterprise customers, large ones, financial companies, pharmaceutical companies, utilize today in production. This agentic AI is something that serves endless production clusters for investigations. We're expanding capabilities of this every day. Every time you attend one of these sessions and you learn more about agentic AI, you'll quickly realize that it moves very fast. The foundational models are improving every day, and the capabilities and things that they are able to do is extremely powerful. Even I was a skeptic years ago, and now I'm a total believer, and I've seen the power of it. Give it 6 more months, and it converts more and more people, and then we realize that it's not going anywhere, and this is something not only do we need to embrace, but something that is very powerful in the right setting. We developed our agentic AI Cloudia in such a way that you could easily introduce change to it. As your organization changes, so can our agentic AI that you're using. Now, a couple statistics about it, and again, it's moving so fast that even this slide is a little outdated. This has over 4,000 different active workflows. It says 12 total agents. Today, there are over 50 different agents that we have developed to be subject matter experts in various facets of Kubernetes. Average latency, which just means the time in which it takes for this agent to recognize that there's an error and give you a resolution, was under 90 seconds, under 1.5 minutes, compared to hours that it may take to triage various logs and so forth. And it has a 99.2% success rate. So the question is, how do you actually know it's any good? And this doesn't just pertain to the agentic AI that we built. Many people are building on their own, which is totally fine. And when you do so, how are you going to know that you have built it in such a way that is effective, in such a way that is tailored to the needs of your specific business? And how we do that is we have a gold standard, which is just benchmarks. We have various scenarios that are real-world ones, sampled from that 1 million incidents that I talked about, and we benchmark how well did this do in this particular scenario. Was it able to get these edge cases right? We had shadow agents, which is a funny way to say we ran multiple agents alongside each other in parallel to test them. Which one did better for what scenario? Why? Basically A/B testing on steroids. We had LLM as a judge. So basically a dedicated agent judging the other agents, being able to cross-reference each other, finding out what it was good in so that they can improve each other. We did a hybrid model. When I say hybrid, that means a couple different things, but not LLM only. So we had traditional machine learning involved that would cancel out some of the noise and be able to feed the LLM only the relevant data to those specific issues. We also have human in the loop. We're working on having auto remediation as well, which does exist to some degree. But having that hybrid model of machine learning mixed with the LLMs mixed with human in the loop creates a very powerful, very efficient, and a very safe environment. Many of our customers today are using this in sandbox environment fully autonomous and not having human in the loop. And in production, they're putting humans in the loop for approval purposes and to verify data and even to update their run books. Maybe they're using it to reverse engineer and create their own golden run book that we failed at. Now, some final thoughts, especially if you want to go down this journey of implementing agentic AI. I started the presentation convincing everybody, let's see if we can build the ultimate flowchart. And now I've switched everybody to let's build the ultimate agentic AI fleet. Building is difficult. When we utilize AI and we build different agents, that can introduce a lot of different things. Technical debt will exist and does exist when building agentic AI. The need to adjust them, to refactor them, to update them to the latest and greatest models or the latest and greatest capabilities. It takes ongoing maintenance. For the same reason you purchase SaaS is going to be the same reason that you purchase SaaS that also includes agentic AIs. So keep that in mind. These things cost engineering hours. These things have toil to them. And it can be a headache. Less so than trying to build that perfect flowchart, but still there is risks to this. It's also a very sensitive environment we're messing with. When we're talking about production and we're talking about lowering your mean time to recovery, these are very important elements. These are elements that you have to get right and in a timely manner. So if you do so and it's not accurate, you've failed. And so keep that in mind. It is very possible, it's very progressing, and it will only get easier with time. I want to thank everybody for coming to my presentation today. Hopefully I didn't bore people too much. We do have a booth set up out there. It has a raffle. We're raffling away a giant hammer, as you see here, and a shield. So please, if you haven't already, go grab that raffle. If you have questions for me or any of my colleagues, we're always happy to answer those questions, to hear more about your either adventure in building your own agentic AI fleet or in utilizing something like we offer here at Commodore. So please stop by. I also have this QR code if you want to see our website and learn more. But thank you, everybody, for your time.